On Wednesday, we talked about the fundamental theorem of algebra and its bigger brother corollary, the complete factorization theorem. We missed that. The pearl of wisdom is that a polynomial of degree n will have n roots. So we have a polynomial, say degree 5, we have hope that we will find 5 roots. That's the hope. Now, I don't know if I said it in this class, but this book has a lot of overlap. And after last class, I'm feeling that's not such a bad thing, because I went over some stuff that we had done. Definitely got the idea that it didn't sink in the first time. So, opportunity for it to sink in a second time. Now, in the context of complete factorization theorem and complex proofs, we're going to take one more look at factoring by grouping. What to say? Well, let's just put the example up. This is kind of a shot in the dark method. You need to have an even number of terms or grouping wouldn't really work. And even then, probably won't work most of the time, but it might sometimes. So again, the strategy is find some way to group these, typically from highest exponent to lowest, and then to group it. If you had 6 terms, you might group it 3 and 3. You might group it 2 and 2, and 2. But this is again, kind of the simplest type of example. Then you factor as best you can. So what are the factors of this first group? X squared plus. Now, I don't know if anyone here has a problem, but some of the other class, when I wrote this, they missed this maybe not perfectly obvious, but crucial point that this is 1 times x minus 3. That's crucial when I want to take this factor out, because I'm left with x squared plus 1 times x minus 3. I don't know if that helps you. Good. If you saw it already, even better. And now we know right away that one of the roots is going to be x equals 3 because of this factor. But now we're stuck here. We have this x squared plus 1, which we referred to previously as being irreducible, not reducible, irreducible. But of course that was under the constraint that we were dealing with real numbers. Now we're dealing with complex numbers, and we know that there have to be 2 roots hidden in here. So the question is, what are those roots? John? that's good. Yes, it's going to be complex. Maybe it'll be pure imaginary, maybe not. But it'll definitely have an imaginary component. So, does anyone remember how you factor x squared plus 1? This also is an important pattern. Think of it as a squared plus b squared, which again is irreducible under reals, but with imaginaries, it's not. How about someone in the second row? Anyone in the second row remember how you factor a squared plus b squared? It's a little tricky until you kind of see how it fits in with. It kind of fits in with this a little. Squared minus b squared. This everybody knows how to factor. Right?
For a squared plus b squared would be ab squared?
A squared plus b squared.
Or would be a plus b squared?
Yeah. Yeah, that's so common, it's wrong. That's so common it has a name. It's called the freshman's dream. A plus b squared is a squared plus b squared plus 2ab. You got to get rid of that somehow. This manages to get rid of it, right? Right? A plus b times a minus b, right? A squared, b squared, and in between you get plus ab and minus ab. So that's how we get rid of it here. We can't get rid of it there. Okay, anybody in the room, anyone have any idea how you factor a squared plus b squared? Because we did see this before. Yes?
Is it a squared plus 2ab plus b squared?
Okay, remember we're trying to factor it. We're trying to get two things multiplied that equal this. So there's three terms. Actually, it doesn't really. This is a plus b squared, right? It's that pattern. Yeah. These patterns are important. Yes, Alex?
So a plus b squared minus 2ab.
A plus b squared
minus 2ab.
Now, you are absolutely correct that this is equal to this. But this is a sum. We need a product. We want to multiply two or more things together to get this. And we can use complex numbers. Yes?
X minus I, x plus I.
Let's see what this is about. We were talking about a's and b's, but we were also talking about x squared plus 1.
Sorry.
So let's go with it. Let's see what this, whether this fills the bill in any way. So let's FOIL this. It's x squared on the front, minus I squared over here. Outer is plus ix Inner is minus ix. Aha, we got rid of that. That's good. Oh, minus I squared. Well, I squared is the square root of negative 1 squared. So it's negative 1. So we have minus negative 1, which is plus 1. So we have x squared plus 1. Oh, yeah, that's what we wanted to do. Very good. Okay. Excellent. But not perfect, because I still want to know, this should be easy now, how to factor this. I mean, it looks like this. X squared looks like a squared. 1 could look like b squared if you multiply 1 times 1, right? You probably only accidentally put your arm up that way, Jessica, so it was probably an accident, but did you have an idea? No. All right. The audience today. This is hard, especially the first time. Well, what did Jay tell me? He had an x plus something and x minus something, right? The a was like the x. Well, there's got to be some b's over here, right? But we know that's not it. That would just be a squared minus b squared. What could we add to the b so that it doesn't become a minus b squared? You want what, I squared here?
I of those keys. Put i's into both keys.
Oh, I. Okay, let's try that. So, again, I'm going to FOIL it, a squared. Plus bi minus bi, that's minus b squared I squared. That's looking like outer, inner, outer, I don't care. Outer negative ABI, inner ABI. Those cancel. Now I just have to look at this carefully. I squared again is minus 1. Minus plus, so that's a squared plus b squared. So yes, this is the magic pattern you want to know when you're trying to find factors of that irreducible. Let's try one more. How about 2x squared plus 5? What are the factors of that? I added something to fool you a little, but you really shouldn't be too fooled. Want to guess here? Want to guess? You can say no. No. Okay. Nate, you have a guess?
Two products together.
I want to factor this. Two things to get this. Knowing this, it worked real well here. We threw in a little monkey wrench, right? But not really. Yes.
2x plus 5i.
Plus 5i.
And then 2x minus 5.
Well, you don't want 2x here, is that right? You want x minus I? Is that your guess? That's a good guess. Let's try it. Say 2x squared, and the outer is minus 2ix, and the inner is 5ix, and then minus 5I squared, which is going to be plus 5. So that's pretty close. We got the 2x squared and the 5. These two drop out. So it was good. That's actually a pretty good guess. No. Now, in the 60s, by that I mean 1960s, if you read your history books, you know, students became radicals. They were unafraid of radicals, so they became radicals. Now students apparently are afraid of radicals. I don't know why. That's the biggest hint I can give without going right to the answer. Somebody. I see a hand, yes.
So I wrote it as root 2 at times x plus root 5 times I.
So you apparently are not afraid of radicals, right?
And then I wrote the same thing again, but with subtract instead of adding them. Oh, but there's the I.
Oh, yeah, forgot the I. Thank you. I mean, what you have to get your head around is that 2 could be a squared, right? Right? If 2 is a squared, and a is just square root of 2. Same with b. B could be 5. B squared could be 5. B is square root of 5. So that's how we can factor this guy. Okay, we're getting there. We're getting there. This is getting better. So let's go back to, we did a lot of extra stuff here. Let's keep it in your head. Let's finish this up. What did we say? Jake came up with this. X plus I, x minus I, x minus 3. So we have 3 roots. What are the 3 roots? Kenny, what are the 3 roots? Give me one of the roots.
3, I, negative I. Oh.
Okay, I'm getting you all. 3. It's not 3. Lazy 3. I and negative I. Does everyone see that? If I plug in 3, this is 0. If I plug in I, this is 0. And if I plug in negative I, this is 0. So these are the roots of that polynomial. And we can feel really good about the fact that since it's 3rd degree, we have 3 roots. Complete factorization theorem also tells us there are no more, right? We don't have to wonder if you could put some weird x in and multiply these and get 0. Okay, so that was grouping. We saw grouping again. Now we're going to see another technique we've used before. Rehashed. Is using the rational root theorem. Another chance, make sure we know how to do that, but now in the context of complex roots. So let's look at e of x equals x cubed minus 2x plus 4. Okay. So the rational root theorem is going to tell us some values that could be roots. It's going to tell us all the possible rational roots. How do we figure that out? Well, we have to look at leading coefficient and the constant term And we're looking for things that might be factors of these on the top and the bottom. So what are the possibilities? Yes, just one.
So for the first one, x, it'd only be 1. So it'd be plus or minus 1 for x.
I'll accept that. Plus or minus 1, that's 2. 2 possible roots. Alexis, can you give me another possible root? Remember, it's got to be a factor on top and a factor on the bottom. What are the factors of 4? Somebody? 2 and
2 and
4.
Yeah.
Right, that's a factor. And 1. Daniel ordered. Okay. So Justin, what's the fact? What's one of the possible factors that I haven't written down already?
2 over 1?
Yeah, 2 over 1. In fact, plus or minus 2 over 1, right? Okay. Devin, do you know what the last 2 roots, possible roots are?
Is it plus or minus 1?
Absolutely. Okay, good. So now we only have 6 possible roots to try. We could find 3 roots among them. We can't find any more. We could find none. But, you know, we're giving it a shot. Okay, so let's start easy. Let's try 1. So we got 1 minus 2 plus 4. That's 3. So good. Try minus 1. Minus 1 plus 2 plus 4. 6 is 5. No, that's not equal. Okay, sorry, Daniel. You didn't win. I'm done. You did. They were possible, but they didn't work out. How about 2? So that's 8 minus 4 plus 4. You just plug in 2. Well, that's 8. That's no good. So the plus 2 is out. All right, minus 2. Minus 8 plus 4 plus 4. Oh, we have a winner. Minus 2 is a root. Okay. At this point, we know one of the factors is x plus 2, x minus a minus 2. And we know, there'll be something else here, some other polynomial, some q of x. So we want to, we could just continue plugging in. And you may want to do that. In this case, that 4, that's 4. 16, 64 minus 8 plus 4, that didn't work. I plug in 4, negative 64, we're nowhere near it. Oh, they're not going to work. So what we want to do is we want to divide p of x by x plus 2, which we have 2 techniques for doing. Blake, do you remember either of those, the names of those 2?
Could we use a quadratic formula? Because it's a 3rd degree polynomial, and we've already found one of the factors.
This is 3rd degree. We want to divide it by x plus 2. It's like quadratic formula a little too much.
Could we do synthetic division? Could we do synthetic division?
Synthetic division. Or Sandro. Remember the other technique? Remember what we call it. Okay, that's all right. Just a name. You want to answer Alan?
Long division? Long division?
It's called long division. Because it looks like long division of numbers, right? Okay. as I've stated at least twice, synthetic division is nice because it's easy, but it's redundant. You can always use long division, and you can't always use synthetic division. But that said, we can use it here because we just have a root, a linear term we want to divide by. We're going to now take offers from the audience. Eleanor, which of those two would you like me to try? Long division or synthetic?
Long division.
You'd like long division, okay. So, x cubed, and I want to write in my x squared term here, even though it's 0, because if I don't, well, actually, if you're doing this with synthetic division and you forget this, which is easy, then you're really a creep. Okay, x plus 2, let's go. This is x squared, so x cubed plus 2x squared. See why that was important to put there? 0 minus 2 is minus 2x squared. It's 2x. Okay, x into minus 2x squared was minus 2x times. And it's 2x squared. Minus 4x. Minus 2 minus a minus 4.
2x.
Minus 2 plus 4, 2x. Some people have trouble with that. Corrected in the exam. And he had trouble with that. Okay, one more. 2x plus 4. I get 0 remainder. I better. If I don't get 0 remainder, either this is wrong or I did something wrong. Okay, so now I know my polynomial is x plus 2 times x squared minus 2x plus 2. All right, let's get rid of this. Now, as much as you would like to answer the next question, you already have, and you gave the correct answer. So, just, know I got it right, and let someone else try. Okay, so this is still x squared. This is still second degree. We don't know the root yet. We could try factoring. X. So this can only be 2, and this can only be 1. And this is a plus, so they're either both plus or minus, but that's fine. They have to be both minus. But then that would be minus 1, and minus 2 is minus 3. Ooh. Uh-oh. So, I'm running out of room here. But then, remember what Blade said. I'm hypnotizing you all. You remember what Blade said. One of you raises your hand and says, I remember what Blade said. Yes, Marco? Quadratic equation. Quadratic formula. Yeah. Right? I can use the quadratic formula on this. I can find the roots, and that'll tell me the factors. Everybody good on that? Connection here? Roots, factors, roots, factors. Okay, so A here is 1, B here is -2, C here is 2. So my negative B is plus 2, plus or minus the square root of B squared, that's 4. Oh, it's going to be minus A times 4 times a times c, that's going to be minus 8. That's looking imaginary. All over 2a. Or 2 plus or minus the square root of 4, negative 4 over 2. Or 2 plus or minus 2 times the square root of minus 1 over 2. Or 1 plus or minus square root of minus 1, which is I. Okay? So, I know the roots of this. What are the factors? It's going to be x plus 2. You already found that. What's another? Yeah. What's another factor? I know the roots. What's the other factor? What's the next factor? I know, actually, you know, I apologize. I know a little, it's kind of like medicine. It's like if you have a big room and you're sitting there and you're thinking hard and then you get called on, you get this boost of adrenaline like, I'm on the spot. Everybody gets put on the spot. And that can like drive your brain cells crazy because now you're ready to run out of the room and run away from whatever's going on. It's fight or flight, right? Thank you for not coming up to me yet, by the way. That's hard, but that's okay. Sometimes it wakes you up if you're sleepy. Like if your teacher calls on you, like, oh, I'm awake now, but I don't know what he said. I had a class in college where there were 6 students in the room at 8 in the morning. I would fall asleep all the time. And the professor would say, he had a southern drawl. He'd say, well, Mr. Shumra, why don't you go downstairs to the lavatory? Throw some cold water on your face. You could say that. I would kind of go down there. It would work. I would wake up a little. And then as I came up the stairs, I'd always hear everybody laughing hilariously. I have no idea why. That helped with the adrenaline too. Okay, come on, somebody. What's the root? When you have a root, what's the factor? Yes?
X minus 1 minus I.
X minus, I'm going to write this carefully, 1 minus I. Okay. That's 1, thank you. The next one should be easy. Yes, Marco?
X plus 1 plus
Plus 5. Okay, all right. In my next lifetime, I will become a dentist, so I can, you know, really pull teeth. I could like also, you know, distribute here the minus. So minus 1 plus I, x minus 1 minus I. Now, because it'll come in handy later, I want to point out something. Have we talked about what a conjugate is? Little. We talked about, like, if you have something like this, 1 plus the square root of x, and you want to get the square root out of the denominator, you multiply by something called conjugate 1 minus square root of x, then you have to multiply by this. And you get 1 squared minus square root of x squared, you get 1 minus x squared. We call that a conjugate, but we reuse that term here to describe these two roots, 1 plus I, 1 minus I, or rather, we have this idea of a complex conjugate. If you have A plus B bi. Its conjugate is a minus bi. We just saw that a few minutes ago, didn't we? We were trying to factor a squared plus b squared, right? And it turns out that the factors are a plus bi and its conjugate, a minus bi. Okay? So here we have x minus a root and x minus its conjugate. You know, I know most of you saw me use the quadratic formula and we did the roots thing, but you might be a little suspicious of this. You might. And just in case you're a little suspicious, I think it's worth taking a minute. Let's multiply it back again. X minus 1 plus I times x minus 1 minus I. All right, I'm just going to do some long multiplication here. All right, let's go. Minus I times I. That's I squared, look at the minus. I squared is minus 1 minus plus 1. This is minus I. Oh no, minus and minus plus I. And minus I x. Now we have minus 1 times I. So minus I. Minus 1 times minus 1. Running out of room here. That's a 1. Oh, put that there. And minus x. And then finally, x times I, ix, negative x, x squared. Okay, so what's going to cancel? These are going to go away. These are going to go away. That's good, because I need to get rid of all my i's. And I have x squared minus 2x plus 2. Yeah, that's what I wanted it to be. You should try that once or twice in your lifetime. Just, you know, make you feel like, yes, I didn't just make it up. Okay. So, here we go. So now we have this fully factored, and so we know the roots are x equals, what are the roots again? Ashley, do you know any of the roots?
1 plus or minus I.
That's 2 roots, 1 plus I, 1 minus I, okay. We're looking for 3 though. Mansa, do you know what the third one is?
Sorry? No, sorry, can you?
I'm sorry,
I was asking for say it again.
Oh, I was saying, what's the third root? This is the factorization. You got I plus 1 and I minus 1. What's the third one?
I'm not sure.
It's okay. Blade,
Negative 2.
negative 2, yeah. Because we have this factor here, right? That gives us a root of minus 2. Okay. And hooray! Oh, I don't have it written down. Complete factoring theorem says there should be 3 roots. We found 3 roots. Complete factoring theorem tells us one other thing. There are no other roots, right? You know, if you thought maybe there's something else we can plug in here to get 0, no way. So, okay. So that's rational root theorem, redo, complex roots. Okay, Now that's most of it. There's a few little nits. Here's a nit. E of x equals x minus 1. Okay. Daniel, look, give me a root of this polynomial here.
1 u.
Yeah, 1's a root, yeah. Someone want to give me another one? Yeah, you see, here we have to amend our complete factoring theorem. See, I know the factors of this. They're x minus 1, x minus 1, x minus 1. Hey, son, can you tell me another one? This is a trick question. Alex, another one. Factors are x minus 1, x minus 1, x minus 1. Henry? Another factor?
No, just one. Is it all just one?
Well, yeah, but it's not. I'm looking for a factor, a linear factor, one with an x in it. Yes, Daniel?
Oh, it's not like a. You said with an x in it?
Yeah.
You mean for the factor or for the?
I'm trying to factor this.
Okay.
This is total trick question here. Once you see what I'm doing, you go, oh, why was he being so weird? Christina, you see another factor in this? I got 3 factors. Can you see the board? Okay, it's a 5. Right. Yes?
2 more, x minus 1?
I only asked for 1 more, but all right. You ruined it for somebody.
Oh, sorry.
You know? Yeah, you should be ashamed. Yeah, these are the factors. All the roots are 1, right? Okay, so we have to amend the complete factorization theorem a little. You have to count roots and their multiplicities. Multiplicities. This has just one root, one distinct root. But it has multiplicity 5. So given that I count 1 5 times, I've found all the roots for this. That's that little nit I was telling you about. You gotta be, you know. If I said, give me all 5 roots of this, you might get upset and say, I can only find 1. Well, there's only 1 distinct root. Okay, with that in mind, let's look at another problem. Here we get to reuse another little strategy that we did maybe a week ago or so. Okay, I want to factor that. Someone start me off. Someone who wants an easy question. Who wants an easy question? Go ahead. What can I factor out of this? Here.
3.
Okay. We can stop there. You want to go further?
He said 3x.
Who said 3x?
I don't know.
That's okay. Let's do 3x, all right? We'll give you credit, you know? He wasn't called on, right? You get full credit. All right. 3x to the 4th plus 8x squared plus 16. Okay. Now, this, by now, if your brain isn't kind of going, aha, that's 4 squared and that's 2 times 4. We're looking for that pattern, that perfect square pattern. The only thing is, here we've got an x to the 4th and an x squared. Remember I mentioned a disguised quadratic, right? If I were to substitute here y equals x squared, this would become y squared plus 4y plus 8y. Oops. 8y. And then this is a perfect square, right? It's just y plus 4 squared, except we don't really care about y, we care about x, right? So we could just skip all those steps and just go to 3x times x squared plus 4 squared. Okay, making progress. What about this? Richard, what do you think I can do with this x squared plus 4? Got any ideas? Okay. Yes, Marco? X plus 2I. Oh, you mean the squared here? It's real important where you put the square. If you put it here, it doesn't, it's not what you want. Okay. If there was just 1 here, this would be x plus 2i, x minus 2i, right? But it's squared, so each of these factors is twice. Okay. All right, progress. All right, so now we've completely factored it. So what are the roots? Evan, can you give me a root? Okay. Jessica, can you give me a root? Remember, I factored this. That's my polynomial. Okay, factor. Make this connection, right? If I've got a linear factor, I know a root. Selena? Just one.
0.
0, okay. All right, I've got 3x. If I plug in 0, everybody see that? Plug in 0, it's a root. Okay. Another root. Another root. If I plug in negative 2i here, I get 0. Okay. One more root. I want somebody. Thank you. Okay. Now, let me ask my question because you already have the answer, I think. I have 3 roots, but I have a 5th degree polynomial. So I'm missing 2 roots. Where? Oh, is that the question? Is that you wanted to answer?
I wanted, yeah.
Yes. Okay. Where are those? Tell me where one of those roots is.
Well, it's the multiplicity of negative 2i.
Okay. And for someone who wants the easiest question today, if you're paying attention, where's the other one?
The other multiplicity.
Yeah, the other one. Yeah. Okay, so I've got 2 roots of multiplicity 2. 2 plus 2 plus 1, 5. Just what the complete factorization theorem tells me. Hooray! Mathematics is consistent. It works. All right. Okay. Okay, now a problem which is just it's kind of a small little puzzle. The answer embedded in what we've already done. If I knew the roots of a polynomial, I have some polynomial, and I want to know the roots. I'm sorry, I do know the roots. I have some list here. I have C1, C2, C3, etc., C to the n. I know that it's easy to make a polynomial with those roots. It's just x minus c1, x minus c2, all the way to x minus c to the n. So this is obvious, right? Any of these values I can plug in, because one of these terms will be 0. But that's not the only polynomial that's true of, right? So like I could just say, 3 times that. All those roots still work, right? Or I could put some other number there. I could just put a constant there, right? A. As long as a is not 0, that polynomial works. Well, okay. What if the polynomial I want to get out of here, I want to restrict it. I want to say, I want it to have real coefficients. So, for example, if one of the roots was, say, 2 plus I, well, I would have a factor, x minus 2 plus I, but I want to get rid of the I, because I don't want it left when in my coefficients. So the question is, how can I get rid of that 2 plus I? We already had a hint earlier when we talked about, I didn't write it down, complex, good time to write it down, complex conjugate. Remember, if you multiply a complex conjugate, if you multiply a complex number by its complex conjugate, what you get is real. In other words, a plus bi times a minus bi, you just get a squared plus b squared. That's a real number. So the strategy here is, if I have something that looks like this, if I multiply it by a term with its complex conjugate as a root, so that would be minus 2 minus I, then I can be pretty sure I'm going to get rid of those pesky imaginary numbers. Keeping that all in mind, here's a problem. I want to find well, we're going to do the easy one first. I want to find a polynomial with roots in my c's I, negative I, 2, and negative 2. And I also want p of 3 to be 25. So how would I go about that? Well, I'm going to leave this constant in here because I don't know what it is yet. But I know I'm going to have x minus I times x minus minus I, x plus I. I'm going to have x minus 2 and x minus minus 2, x plus 2. And let me do a little multiplication here. X minus I times x plus I. That has to be what? Say it. X minus I times x plus I must be. It's going to be x squared plus
Plus 1.
plus 1. Exactly right. What about x minus 2 times x plus 2? Who haven't I called on today? Joshua? You know x plus 2 times x minus 2?
X squared minus 4.
X squared minus 4. Right? All right, I'm going to do the hard work here for you. X squared minus 4 times x squared plus 1. So that's x squared minus 4 times minus 4x squared, x to the 4th. Okay, so we have a times x to the 4th minus 3x squared minus 4. So that's my polynomial, almost. But I wanted p of 3 to be 25, right? So p of 3 is 25, and that's equal to a times what? 3 to the 4th, 81, minus 3 times 3 squared is minus 27. 4. Well, rather than subtract 27 from 81, because I have to do a carry in my head, how about I add minus 27 and minus 4? That's minus 31. Ah, that's easy. 8 times 50 equals 25. So now I know my A is 25 over 50, or 1/2. Now I know polynomial is 1/2 x to the 4th minus 3x squared minus 4. Okay, that was the easy version. The hard version isn't very hard. It's the same kind of problem, but add a twist. See, I want the solution to have real coefficients, but I don't care about what p of 3 is, but I do want the roots to be 1/2 and 3 minus I. Okay. Well. So one of the roots has to be x minus 1/2, or like 2x minus 1. That's a little easier. Still, you plug in 1/2 to get 0. One of my roots is x minus 3 minus I. But I want the coefficients to be real. I don't want any imaginary coefficients. So how am I going to do that? How am I going to get that to work out? Is there any way I can do that? I can guarantee that I get rid of this I here. Yes, Nate?
3 squared.
I is I squared.
What do I want to square?
So I squared.
The I. So it becomes
Well, squaring, yeah, it's inside what I'm going to do, yeah. But what I really want to know is, what can I do to this expression? Because this is, right, this is a polynomial with roots 1/2 and 3 minus I. I want that. What do I have to do to this so that those coefficients become real, imaginary stuff goes away? And you're right on the right track. You want to multiply I by itself. But we want to do it in a way that, see, if I just multiply this by I, right, we'll get rid of that I, then we'll have 3 i's, right? How do I do that? Let's try that. So x minus 3 minus I times 3 plus I. Well, 3 plus I times the conjugate is 9, plus 1 is 10. That's good, you got rid of the I. But now we have 3x plus I. So we still have a pesky I to get rid of. You're on the right track though. What do we have to do here? Great, we're about to run out of time. So we have to tell you the secret. Let's just add another root. Okay. The thing you want to notice here is that when you have a polynomial with real coefficients, but it has some complex roots, they come in pairs. Always get the conjugate with the other root. I think that's going to be it for today. Okay. There's a homework assignment for Monday.